Sustainable chemistry focuses on the design of processes or products that use or generate less waste or hazardous substances. This is important as it is aligned with the current efforts to fight global warming. As such, I present to you our contribution towards sustainable and ethical chemistry. Good day. My name is Thabang Ncongwane, under the supervision of Dr. Smith and Professor Ndonsa at the University of Johannesburg, South Africa. Thanks to the VCCA organizers for this opportunity. Our presentation outline is as follows. Flavonoids are a group of naturally occurring polyphenolic compounds. Treatment-related derivatives have been reported to show improved biological activity, and as of recently, more than 10,000 of these compounds have been identified and documented. These compounds are commonly found in plants and are obtained by extraction. Therefore, a technique known as derivatization is commonly used to study these compounds. In this technique, the compound's chemical and physical properties are altered to improve their performance in chemical analysis. Examples include alkylation, acylation, and cellulation, which was used in the study. In cellulation, the acidic proton of the hydroxyl amine or thiol group is replaced with the cellular group of the cellulating reagent. This offers benefits such as it is rapid, it improves compound thermal stability, and also it lowers the boiling point of the compound. And it also results in minimal artifact, which is important in terms of chromatographic analysis. This brings us to our problem statement. Most flavonoids are polar, less volatile, and thermally unstable. They also have similar chemical structures, making them very difficult to separate. This is ideal for high-pressure liquid chromatographic analysis. However, HPLC uses large amounts of organic solvents, thus it is unsustainable. Alternatively, less chromatography can be used. However, GC is only suitable for volatile and thermally unstable substances. As such, to expand its application to polar compounds, derivatization, specifically cellulation, is commonly used to make them or these compounds amenable for GC analysis. Like any other technique, it has its own limitations. Derivatization introduces extra preparation steps, leads to poor selectivity, and also uses expensive hazardous chemicals. In most laboratory settings, these reactions are commonly performed in batch, which is tedious and time-consuming. Therefore, to address the above limitations, we have adopted a few sustainable technologies to align derivatization with green analytical concepts. The first one is known as 3D printing, or additive manufacturing. In this technique, an object is created by stacking layers of material in a layer-by-layer sequence. Compared to other manufacturing techniques, it offers benefits such as it is inexpensive, and also the manufacturer's devices can be rapidly customized and reused. 3D printing can be and was used to manufacture microfluidic devices. These devices are used to exploit the physical and chemical properties of liquids and gases at micro or nanoscale. The benefits such as diffusional mixing, efficient heat and mass transfer, and also high surface-to-area ratio are achieved. This means reactions that are commonly or require harsh conditions can be safely performed rapidly, making microfluidics ideal for continuous flow chemistry since it uses small amounts of reagents. Flow chemistry is concerned with conducting reactions in continually flowing stream by means of tubing or channels. This opens possibilities for automation of batch procedures, including safe upscaling in terms of industrial applications. The advantages of such systems include safe reactions, precise control of parameters such as temperature and stoichiometry. These systems are also inexpensive, which is another advantage. Having a leak-tight system is crucial, and I am sure that all chromatographers here can appreciate this. A continuous flow system typically starts with a sample or reagent delivery system. The stream can be mixed, Therefore, before reaching the reactor, although this step can be incorporated into some reactors. After the reaction has taken place, quenching and pressure regulation may be necessary, and again, this might be incorporated into the reactors itself. This is followed by fraction collection. Lastly, purification and phase separation steps may also be required prior to analysis. There is a variety of reactors that can be used as shown on the diagram on the screen. A PET-bag reactor is typically have a solid in a chamber through which a gas or liquid typically moves, similar to a high-pressure liquid chromatographic column. A coiled reactor is literally a column or a coiled tube in which the chemical reactions or interactions take place, not like a GC column. On the other hand, a stirred tank reactor or continuous stirred tank reactor can also be used. It consists of one or two inlets for introducing a sample and reagents into the tank that is continuously stirred. The reaction mixtures access the tank through an outlet. Another important reactor is based on the device that contains small channels in which the reaction can take place. These are sometimes referred to as microfluidic or millifluidic devices, depending on the channel diameter. In this sense, scalability is also always important because a large amount of product may be synthesized. However, in analytical chemistry, we often want to scale down in the opposite direction to produce smaller systems that require less samples and less reagents. This brings us to the aims and objectives of this study. The aim of the study is to automate derivatization procedures with a focus on the cellulation of flavonoids. To achieve the aim, the following objectives will be met. The 3D printed device will be developed. The model compound, which is quercetin, will be derivatized within the 3D printed device. Isolated flavonoids will then be derivatized as the model compound was derivatized in the device. And finally, the plant extracts that are chemically complex will be derivatized in the same device. In developing 3D printed microfluidic devices, we used a technology known as fused deposition modeling. Here, we designed the devices using Fusion 360, which is an open source computer-aided software. The devices were then printed using a chemically resistant and transparent polypropylene filament. The derivatization of quercetin was performed using N-methyl tertiary butyl dimethylsilyl trifluoroacetamide, also known as MTB-STFA according to the schematic shown. Pyridine is commonly used as a catalyst or promoter of cellulation. However, due to its hazardous nature, it was substituted for acetonitrile to maintain the sustainability of the study. From the batch to the flow reactions, when designing our reactors, we also need to consider the type of reactions that is required. In a batch reaction, liquid-liquid extraction can be done in separating funnels, although this will require large amounts of solvent. On the other hand, robotic autosamplers can mix reagents as desired directly into the vials. To convert these batch reactions into flow reactions, we learned that a two-step approach provides for a smoother transition. The continuously stirred tank reactors are used in preliminary experiments. These reactors could be classified as batch inflow systems since the tank volume is relatively large, of about 1.2 milliliters in volume, and thus it is similar to performing reactions in vials. The difference is that there is a constant flow in and out of the tank. Once the flow rates are optimized for constant stirred tank reactors, it can then be translated to channel-based devices. The length of the channels can be customized to obtain the required residence time, and some steps can be combined, for example, by incorporating a mixing zone or adding an additional inlet for quenching the reaction. For our batch method in this study, 100 microliters of quercetin was dissolved in acetonitrile Quercetin, a powder, was dissolved in acetonitrile and dioxane mixture, and then that 100 microliter was derivatized with 100 microliter of MTBS-TFA in a GC vial. The sample was voted for 5 minutes and subsequently analyzed. And for the continuous flow reactions, the system consists of two syringe pumps that act as delivery systems. The flow rates are controlled by a computer. Therefore, syringe A, as shown on the screen, contains the sample and syringe B contains MTB STFA. The two were introduced into a microfluidic device via tubing, which enters the device via the threaded inlets. Where A and B mix and interact, the device channels are less than 1 millimeter in internal diameter, and the device has a residence time of about 3 to 5 minutes. 3 fractions were then collected into the GC vials and subsequently analyzed with the techniques to be named later. So initially, we ran TLC for both batch and continuous flow samples. The plates were developed in a 9:1 chloroform and methanol mobile phase. We observed that the derivatized quercetin has a high affinity for the mobile phase, which is less polar. This was expected as derivatization reduces polarity by replacing the acidic proton of the quercetin with the silyl group of MTBS-TFA. The TLC also showed 100% conversion of quercetin. The results are also similar to the continuous flow sample. We further characterize the samples using HPLC. What we observe is that before derivatization, only one peak was observed at about 2.5 minutes on the chromatogram as shown on the screen. But however, after derivatization, both in batch and in continuous flow, we observe the appearance of a new peak at about 3.4 minutes together with the previous quercetin peak of the underivatized quercetin. Compared to the previous TLC results, HPLC results in fair and incomplete conversion of quercetin. Although the derivatized quercetin peak has a larger area than the unreacted quercetin. This also shows comparable results for both batch and continuous flow methods. We further then characterize the samples with GC, FID, and GC TOF-MS, which is time of flight mass spec. The underivatized quercetin has been reported to have boiling points of above 500 degrees Celsius. For flame ionization detection, or simply FID, with a maximum oven temperature of about 340 degrees, no peak was observed. After derivatization, however, a peak was observed at about 30 minutes. The main aim of derivatization, as known, is to improve compounds' thermal stability, reduce their polarity, and also make them amenable for GC analysis by also reducing their boiling point. Hence, this peak was associated with the derivatized quercetin. This can be justified by the fact that quercetin cannot be observed on a column at 340 degrees because of the reported boiling point of about above 500 degrees. But as soon as it is derivatized, which is expected to reduce its boiling point, it then shows on the chromatogram at about 340 degrees and 30 minutes, as observed or shown on the screen. We then further characterize these samples using GC TOF-MS as explained earlier to prove our association. What we observe is that two peaks were observed at 18 and 28 minutes respectively. Upon analysis and characterization, we observe that a peak at 28 minutes is characteristic to the quercetin that has been derivatized at least 5 times. Since mass spec is more sensitive than flame ionization detection, the peak at 18 minutes characteristic to quercetin that has been derivatized at least 2 times was only observed on the mass spec. The results for both batch and continuous flow methods are comparable and support the previous TLC and HPLC data. We finally characterize the samples using FTIR, or Fourier transformation infrared spectroscopy. Before derivatization, the peak at 3300 per centimeter, which is characteristic to the hydroxyl group of quercetin, was observed. But after derivatization, both in batch and in continuous flow, we observe the disappearance of the hydroxyl group that has been seen that is characteristic to the hydroxyl group of the underivatized quercetin at about 3300 per centimeter. All the results obtained from TLC, HPLC, GC, and FTIR for both batch and continuous flow methods were comparable, but for the purpose of this presentation, the NMR data was not shown. In conclusion, we have demonstrated a sustainable alternative and semi-automated procedure for the derivatization of flavonoids compared to the traditional batch method. This is crucial for improving throughput and capacity in terms of natural product. Further, the technologies related to the fourth industrial revolution, such as 3D printing, robotics, and automation, were used. Designing of procedures that reduce or eliminate waste is sustainable and it is in line with green analytical concepts. We have also expanded the application of GC for polar compounds, and in future, we want to modify and optimize the system to work on multiple samples with minimal manual intervention using a 6-port switching valve. We also want to extend the system's application to start fuels and food products. By so saying, I would like to acknowledge my supervisors, Dr. Smith and Prof. Ndinja, the Separation Systems Chemistry Group, the Analytical Chemistry Group, the Department of Chemical Science, the University of Johannesburg, the Virtual Conference on Chemistry and Certification organizers, and also the National Research Foundation of South Africa for funding this study. Ngiyabonga, and I thank you, which means thank you in Zulu. Ngiyabonga.